Good afternoon, everyone. Good afternoon. Am I audible?
Yes, sir.
Yeah, Durga Prasad.
Yes, sir.
Yeah. So, in the last class, we had discussed about the operation of a basic comparator and the operation of the comparator in inverting and non-inverting modes. So, today we'll complete the applications also. So, we have 4 applications of comparator. So, first one, zero crossing detector, and the second application is level detector, and the third one is window detector, and fourth one is pulse generator. So it's very important for short answer question. So write the applications of comparator. So you have to write these 4 applications: zero crossing detector, level detector, window detector, and pulse generator, right? So let us discuss briefly about each and every each application of the comparator. So for the first one is zero crossing detector. The first one is zero crossing detector. So in the last class, I already discussed regarding about the zero crossing detector. So it's a basic. It's the circuit of the circuit of the zero crossing detector is looks like a basic comparator. So if you observe the circuit, so I'm giving the non-inverting input V in, and I'm giving the zero reference voltage to inverting input terminal. So if you observe the input and output waveforms, first of all, I'm giving a sinusoidal signal as the input to the basic comparator. So I'm taken 0 volts as my reference. So if you observe during the positive half cycle of your input signal, we are getting positive saturation output, right? So coming to, when it crosses the 0 level, when it crosses the 0 reference level, and when V in becomes negative, right, the output is changes its state from plus V sat to minus V sat level, and the cycle is repeats, right? So what you observe, what from this waveforms, so whenever the input crosses the 0 position, 0 level, the output changes states from plus VSAT to minus VSAT and vice versa. So by using this basic comparator circuit, we can detect occurrence of 0 in the input signal. Occurrence of 0 in the input signal. That's one of the best example of comparator, that is zero crossing detector. Okay. So coming to second application, level detector. So by doing some modifications in the basic comparator circuit, we can design the level detector circuit. So this is also discussed while moving the trip point, moving a trip point. The same circuit here we have. So if you observe the circuit, this is the level detector circuit. If you observe this circuit, right? So here I'm giving an inverting input to my comparator. So if you observe the non-inverting voltage, for this, I'm taking a reference voltage, that is, which is here I'm considered as V level. Here I'm considered it as V level, which is the voltage across R2. So here I'm giving plus VCC, positive power supply, to my pot, I mean potential divided network. The voltage across the R2 I am take it as V reference, which is here I'm considered as V level. Now this comparator, now it compares your inverting input signal with the V level, right? So if you observe the output input and output waveforms, so here I'm giving positive reference voltage. If you observe this one, this V level is applying to non-inverting input of op amp. So that means we are giving positive reference, right? So that's why here I'm representing that positive reference level with a dotted line, right? Whenever the input signal crosses this positive V level, right? Because due to inverting a comparator action, we are getting negative VSAT as the output whenever during the interval, I mean during the period when V in is greater than V level, right? So whenever V in falls below the V level, right? So we are getting output as positive VSAT, right? That means uh, here we know that out the application is level detector, nothing but whenever the input signal, this is the input signal, right? Sinusoidal signal is the input signal. Whenever this input signal crosses the level, if you observe, this is the level line, I mean reference voltage line. So whenever the input signal crosses this V reference level, right? You can observe the changes in the output. First of all, when it crosses the V level, the output is moved, changes to minus VSAT, right? Minus VSAT. Whenever again the input signal is crosses the V level again, the output shifts to plus VSAT. Again, whenever V level, I mean V in is crosses again V level, the output again shifts to minus VSAT. That means we
Sir,
can detect the level of the level. Hello.
sir, screen share అవట్లేదు వేరే స్క్రీన్ రావట్లేదు సార్.
Yeah, wait a minute. Is it clear?
ఓకే సార్.
Yeah. So this is a zero crossing detector, which is basic comparator, right? So whenever if you observe the sinusoidal input, right? Whenever this is the input signal given to the non-inverting input of op amp. So whenever that input signal crosses the zero level, you can observe the changes in the output. You can observe the changes in the output. So initially, when during the positive cycle of input signal, your output is plus VSAT. Whenever the input signal crosses the zero position, that is V reference is zero, right? We are giving zero V reference at zero. Your output shifts from plus VSAT to minus VSAT, it maintains the minus VSAT level. Whenever again the input signal crosses this zero level, again output shifts to plus VSAT. Again at this position, whenever it crosses the zero level, again negative VSAT. That means in zero crossing detector, nothing but the comparator detects the uh, whenever the input signal crosses the zero level, it detects the position, right? That means occurrence, so it detects the occurrence of zero in the input signal. So whenever the input signal crosses the zero, there will be the changes in the output, right? Is it clear, all of you? Is it clear?
Yes, sir.
Right. Coming to level detector, so by doing some modifications, so if you observe the input, I'm giving the input to the inverting input terminal. I'm giving the V reference. Here here I have taken that reference voltage as V level, which is given to non-inverting input terminal, right? What is V level means nothing but VCC into R2 by R1 plus R2, right? So this is I'm giving positive V level, right? So when if you observe the output waveform, input and output waveforms, right? This is the V level. This is the V level. That dotted line represents V level. So if you observe, V in crosses this V level, your output changes state from plus VSAT to minus VSAT. If you observe again, when it falls below the V level, V input, again output shifts to positive VSAT. Again, V in crosses the V level, again output shifts to minus VSAT. That means whenever it crosses to some particular position or some particular level of the input signal, the output changes state from plus VSAT to minus VSAT and vice versa. This is how the comparator used as level detector. Is it clear, all of you? Is it clear?
Yes, sir.
Right. Coming to pulse generator, right? Coming to pulse generator, right? So this is the circuit diagram for pulse generator. So in the circuit, this one is a basic comparator circuit, right? This we are having first part, right? Basic comparator circuit, and the output of the comparator is given to a differentiator, given to the differentiator. So the output of comparator applied as input to your differential circuit. and the output of the differentiated circuit is again given to a diode. So coming to the operation of this circuit, how it generates how comparator generates the pulse, right? So we know that comparator is used as waveform converter. We know that signs, if you observe if you give the sinusoidal signal as the input, we are getting square wave as the output. We are getting square wave as the output, isn't it? Right? Already you observed, right? If you apply sinusoid signal as the input, you are getting square wave as the output, right? Is it clear? Right? Then when you are applying that output of the comparator, which is a square wave, to your differentiator circuit, what is the output of the differentiator circuit for the square wave input? What is the output of the differentiator circuit for square wave input? Output of the differentiator for square wave input. What is the output? Tell me.
Train of impulse.
Right, very good. Train of impulses, right? So we are getting impulses like this, right? Right, like we are getting output like this, train of impulses. So what is the output of your differentiator? Train of impulses, right? So what about the functioning of diode? When you are giving the positive signal, the diode gets forward bias, otherwise it is reverse bias. So that means whenever you are getting the negative impulse, the diode is reverse bias. When the output of the differentiator is positive spike, the diode is forward bias. The diode is forward bias. Nothing but, so what is the output of the diode? Expected output of the diode? What is the expected output of the diode? Like this. It allows only positive spikes. It allows only positive spikes, right? Is it clear, all of you? Is it clear? During negative spike, the diode gets reverse bias. There is no output voltage. There is no output voltage. This is the output voltage. This is output voltage. What is the input for this circuit? A sinusoidal signal. A sinusoidal signal is the input of this circuit, input to this circuit. That is V in. What is the output of the comparator? A square wave. What is the output of this differentiator section? Train of impulses. What is the output of this diode? You are getting positive spikes. Is it clear, all of you? Is it clear? Any doubt? Is it clear?
Yes, sir.
Yes, sir.
Yes,
Right.
sir.
Right. And coming to last application of the comparator, yeah, that is window detector. That is window detector, also called as window comparator. Also called as window comparator. So this is the circuit I have taken from the internet. So here in the window comparator or window detector circuit, I have used two comparators. I have used two comparators. I have used two diodes. I have used two diodes and one transistor and one potential divider network. Okay, one transistor. The supply is VCC plus 5 volts. Okay. So what is window detector? Window detector nothing but this circuit detects whenever an unknown voltage is falls within the specified input voltage band. Okay, so the window detector circuit detects when any unknown voltage is falls within a specified band of voltages, right? So that band is also called window, right? It is also called window comparator. So coming to operation, coming to operation of this circuit, right? So first, we can take three cases, right? The first case is V in is less than VLT and V in is less than VUT. So this is the first case. V in is less than VLT, V in is less than VUT. LT means lower threshold, UT means upper threshold. Okay. VUT means upper threshold voltage, VLT means lower threshold voltage, right? So this is the comparator. So I'm giving input signal to for the two comparators. One has non-inverting input and another one is inverting input, right? So if you observe, coming to the case one, when V in is less than VLT, that means VLT is the input of A2. So when V in is less than VLT, what is the output of A2? Output of the comparator A2. What is the output of the comparator A2 when V in is less than VLT? Here it is the inverting comparator. What is the output? V in is less than VLT. What is the output of comparator A2? What is the output of the comparator A2 when V in is less than VLT? Hello, are you there?
Yes, sir.
Right, tell me. Then tell me, what is the output of A2 when V in is less than VLT? VLT is the non-inverting input, V in is the inverting input, and the circuit and the comparator is inverting comparator because we are giving the input signal to inverting input terminal. What is the output of A2 when V in is less than VLT? హలో చెప్తారా క్లాస్ ఆఫ్ చేయమంటారా?
సార్ క్వశ్చన్ ఒకసారి చెప్పండి.
What is the output of A2 when V in is less than VLT? What is the output of A2 when V in is less than VLT? A2 is second comparator. What is the output of comparator when V in is less than VLT? చెప్పండి.
పాజిటివ్ సార్.
Right. Positive VSAT. Positive VSAT because non-inverting is more compared to inverting input. So output is plus VSAT. That means positive VSAT. So what about diode condition D2? It is forward bias or reverse bias?
Forward bias, sir.
Right. It is forward bias. Right. Coming to A1. V in is greater than VU2. Sorry, V in is less than VUT. What is the output of A1? V in less than VUT.
Minus V, sir.
Right. Minus VSAT. What is the condition of D1?
Reverse bias, sir.
So D1 is reverse bias. D2 is forward bias. So then what is the voltage here? What is the voltage at this point now? What is the voltage at this point when D1 is reverse bias and D2 is forward bias? Right. Plus VSAT. plus Vsat.
Plus Vsat, sir.
Right, plus Vsat. Then what is the voltage at across this R2? What is the voltage across R2? R2 by R1 plus R2 into plus Vsat, isn't it? R2 by R1 plus R2 into Vsat. That is the voltage applied to base of the transistor. That is the voltage applied to base of the transistor. That voltage is plus Vsat into R2 by R1 plus R2. This is the voltage we are applying to your base of the transistor Q. So whenever the voltage, that is a positive, that means saturation voltage, which is whose value is approximately 15 volts, is applied to your base of the transistor. What is the state of transistor? What is the state of transistor? Whenever you are applying this much of voltage to base of your transistor, it goes into the saturation. It goes into the saturation. Saturation means transistor is in on state or off state?
On state, sir.
Right, on state. So whenever the transistor is on state, if you observe this circuit, it becomes like this. Becomes like this. If you observe the circuit, this is a resistor and on, which is connected to ground. You are measuring output here. You are measuring output here. So this is 5 volts. Then what is the output? Then what is the output? This part. What is the output voltage? What is the output voltage? The source is directly connected to ground. What is the output voltage? What is the output voltage? Here the source 5 volts is directly connected to ground. What is the output voltage at this location?
0 only.
Right, 0. This is the first case. If you observe, Vin is this is the what you have taken. Vin is less than VLT and Vin is less than VUT. ఇదే కదా మన first case తీసుకున్నాం, right? So what is the case here? This one, this part. If you observe the transfer characteristic, this is the part, right? So if you observe output, so which is 0, which is, if you observe this waveform, your output is 0 when Vin is less than VLT, means this is Vn equal to less than VLT, and Vin is less than, when Vin is less than VLT means Vin obviously less than VUT. అంతే కదా, Vin less than VLT అంటే Vin is obviously less than VUT. So in the case 1, what is the output? 0 volts. What is the output? 0 volts. Coming to case 2, Vin is greater than VUT. Vin is greater than VUT. Similarly, Vin is greater than VLT. This is the second case. Then tell me, Vin is greater than VUT. What is the output of A1? Vin is greater than VUT.
Plus Vsat, sir.
Plus Vsat. What is the status of D1?
Forward bias.
Forward bias, right? So when Vin is greater than VLT, what is the output of A2? Vin
Minus Vsat.
minus Vsat. What about D2?
Reverse bias.
Reverse bias.
sir.
Then what is the voltage at this point? D1 is forward bias, D2 is reverse bias. What is the voltage at this point? What is the voltage at this point? D1 forward bias, D2 reverse bias. The output of the A1 is plus Vsat. Output of A2 is minus Vsat. What is the voltage at this point?
Plus Vsat.
Right, plus Vsat. Similarly, similar to case 1 only. Case 1 లో మనకి D2 forward bias అయింది, D1 reverse bias అయింది. కేస్ 2 కి వచ్చేసరికి D1 ఫార్వర్డ్ బయాస్ అయింది, D2 రివర్స్ బయాస్ అయింది, రైట్? Then what about the state of this transistor? It goes into the saturation. Saturation means on state. Then what about V0 in this case, second case? What about V0 when it is on state?
0, sir.
Right, it is 0 volts. It is again 0 volts. So if you observe, this is the region where Vin is greater than VUT. ante kada, ఇది Vin, which is greater than VUT. This is the region. Vin is greater than VUT. Right? Vin is greater than VUT. Similarly, at the same time, Vin greater than VLT. This is VLT level, right? This is VLT level, right? So here obviously this region is greater than VLT, right? What is the output here? In this region, what is the output? In this region, what is the output voltage? ఎంత వచ్చింది మనకి?
0, sir.
0 volts. Similarly, ఈ region లో ఎంత వచ్చింది మనకు output? That is the first case. Vin is less than VLT, Vin less than VUT.
0 volt,
Right,
sir.
0 only. 0 only. Now coming to this region. Coming to this region. What is the case? Third case. That is VLT is less than Vin less than VUT. Vin is less than VLT less than Vin less than VUT. దీన్ని మనం ఎలా స్ప్లిట్ చేసుకోవచ్చు? VLT is less than Vin అని, right? Then VUT greater than Vin. దీన్ని ఇలా డివైడ్ చేసుకోవచ్చు కదా మనం ఈ కేస్ ని.
Yes, sir.
Right. Now apply. First, VLT is less than Vin. What is the output of A2? VLT is less than Vin.
Minus V, sir.
Minus V set. What about D2 condition? What about D2 condition?
Reverse bias, sir.
Reverse bias. Right? Right. Next, VUT greater than Vin. What is the output of A1?
Minus V, sir.
Minus
sir.
V set. What about status of D1? What about status of D1? Hello? What is the status of D1?
Reverse bias, sir.
Right. So both D1 and D2 are reverse bias. Then what about the state of transistor? Here, what is the voltage? Both are reverse bias means here, what is the voltage?
0.
Right, approximately 0. Approximately 0. Then what about the status of transistor? On or off?
Off, sir.
Right, off state. Then what is the voltage? So off state means there is no collector current. Off state means there is no collector current, nothing but there is no drop across R. There is no drop across R. Then what about your V0? What about V0? 5 volts. That's why you are getting
Plus
in the
5
third
volts.
case 5 volts output. Nothing but if any voltage falls, that means any unknown voltage falls within a specified voltage band. This is the band. VLT less than Vin less than VUT. We can detect that we can find that voltage level. How we can find the voltage level? Whenever the voltage falls between this band, we are getting output as 5 volts. Otherwise, we are getting 0 volts. So that is the how the comparator is used to detect the some unknown, whenever the unknown voltage is falls within a specified voltage band or window. That's why it is called window comparator. Here I have explained the 3 cases individually: case 1, case 2, and case 3. So if you observe this, so if the voltage is between VLT and VUT, here I have written mistakenly VLT and VUT, window of 2 voltages, V0 is plus 5 volts, and outside of this window means this region, and this region we are getting 0 volts as the output. Is it clear, all of you? Window comparator.
Yes, sir.
So these are the applications of comparator. First one, zero crossing detector, which is a basic comparator circuit. Next, level detector, by doing some modifications like the trip point circuit we have used here. Third one is window detector. For this, we use two comparator circuits and two diodes and one transistor. And the last one is pulse generator. For this application, we use a comparator, a differentiator, and a diode. Is it clear, all of you? 4 applications.
Yes, sir.
సో ఏదైనా ఒక అప్లికేషన్ సర్క్యూట్ డ్రైవ్ చేయమని మీకు షార్ట్ ఆన్సర్ క్వశ్చన్ ఇస్తాడమ్మా, లేదా రైట్ ద అప్లికేషన్స్ ఆఫ్ కంపరేటర్ అని షార్ట్ ఆన్సర్ క్వశ్చన్ ఇస్తాడు. ఓకే, ఇజ్ ఇట్ క్లియర్?
Yes, sir.
సో